the example here at the end of the section, which will notice actually utilize the product rule, because we've got a product x squared times the square root of x squared plus 1. And then because here in this square root of x squared plus 1, we've got the square root on the outside, and then we've got x squared plus 1 on the inside, we notice that we're going to have to use the chain rule here. So we're going to do product rule and chain rule. Okay. But let's write out the product rule, because here we've got the product x squared times square root of x squared plus 1. So we're going to start with the product rule. So here, let me just write out the product rule, and then we can think about how to proceed from there. So we're going to do the derivative of x squared times square root of x squared plus 1 without taking a derivative, plus the derivative of square root of x squared plus 1 times x squared without taking a derivative. Okay? So looking at just these pieces now, this one's easy. The derivative of x squared, it's just 2x. Times the square root of x squared plus 1. Notice there I'm not taking the derivative, but here, the derivative of the square root of x squared plus 1, let me pull this one aside for a moment. We can kind of think about how to approach this one. Because we can think of it now like the square root of x squared plus 1 is really x squared plus 1 to the 1/2 power. So you've got this outer function, right? It's like my outer function is u to the 1/2. So that's my outer. And then my inner function, you got the x squared plus 1 inside of it. So we know that the derivative of the outer function will be 1/2 u to the negative 1/2 power. And then we'll put x squared plus 1 inside, and then multiply on the outside here by the derivative of x squared plus 1. Right, so that's just applying the chain rule to the square root of x squared plus 1. So actually, let's write that down. Let's bring that down here. So we'll have 1/2 x squared plus 1 to the negative 1/2 times the derivative of x squared plus 1. Okay, and then I'll also bring down the times x squared here. Okay, so you see I just kind of am bringing this part down. So that's this here. And then finally, the derivative of x squared plus 1, that's easy now, right? Again, we know the derivative of x squared is 2x, so we'll have 2x times x squared. Okay. One last thing I might do here is just simplify it a tiny bit. I can, for instance, cancel the 2 and the 1/2 here. So maybe a simpler version of this might look like this, where we've got here x times x squared will give me x cubed. And then bringing x squared plus 1 to the negative 1/2 to the denominator. Right, square root of x squared plus 1 in the denominator. Okay. So this is a good application of both the product rule here to begin with, was what the first rule we applied here, and then also here we're doing the chain rule, right? So I hope that you guys are starting to see when we need to use the chain rule, right? And it's always going to be when we have a function on the outside, like the square root of x, or the square root of u being our outer function, and then another function on the inside, which is in this case x squared plus 1. So we have a function within another function, so we can apply the chain rule. Okay, so as a rule, I think that the chain rule is going to be one of the most useful, in that it gets applied a lot, because we're going to see these kind of functions all the time. So over the next few chapters, you'll get a lot of practice using the chain rule. Okay, so from a practical standpoint, it's going to be one that you really want to practice and make sure you're comfortable with. Okay, so let me leave it there for this section. Do you guys have any questions so far about the chain rule? So I'm going to jump right into 3.8, which is looking at implicit differentiation. And so we want to think about how the chain rule might apply when we have curves that are defined implicitly. And what that means is we have a function where, or we have, I guess, a curve where y is not necessarily a function of x, but we can still find dy dx using implicit differentiation. So let me show you guys what that really means here. Take a picture like this, where we've got the equation of the circle, x squared plus y squared equals 1. So this is not a function. It's a, it certainly doesn't pass the vertical line test, right? You can see that if I draw a vertical line here, it passes through the curve at 2 different points. So this is not a function. So when we're looking at the curve that's defined by this equation, x squared plus y squared equals 1, what we might want to know is how we can find the slope of a tangent line to this curve at different points. And one way to approach it is you can look at solving for y in terms of x. So like just solving the equation x squared plus y squared equals 1 for y. Right, so you can subtract the x squared, and then y is equal to plus or minus the square root of 1 minus x squared. So you see here that the plus square root of 1 minus x squared gives me the top half of this circle, right? And then the negative version gives me the bottom half. So these would be now explicitly defining the top and the bottom half as functions. So now if I want to find the slope of a tangent line, well, I can use this explicit form, and we can find dy dx using the rules that we've established so far. Right? In fact, we know how to find dy dx for a function like this just using the rules that we've already done in the previous sections. So you can find the slope of a tangent to any point on this top half using this function, or if I'm finding the slope of a tangent on the bottom half, I can use this other version of it. So what we're going to do is we're going to try and, instead of having to create explicit versions of the curve, we want to be able to work with the implicit form of the equation where we can find the slope of a tangent without necessarily needing to solve for y in terms of x. In fact, what we'll notice is that a lot of times the equations get very complicated, and so being able to solve for y in terms of x is not possible, or is maybe too much work to do. It'll be easier to find a way to find dy dx implicitly. Okay, so that's our goal here. So let's look at an example with this. We've got some function defined implicitly, x plus y cubed minus xy equals 1, which of course is just sort of like this sideways parabola. What we notice is that, of course, it's not a function. It is certainly doesn't pass the horizontal line test or the vertical line test. But instead, what I could do is I could look at the pieces separately and think about what the derivative of f of x is on one of these individual pieces. But we're going to try and avoid doing that, but instead let's think about how I would find dy dx if I have the form of the equation written in this implicit form. Okay, so actually going back to that first example that we did, let's just practice computing dy dx directly from the equation of the unit circle. So, and then what we'll be essentially thinking about here, so before I get to that, I want to think about the picture of the unit circle. We can then find the slope of the tangent line at any point. Okay, so when we say directly from the unit circle here, I want to use implicit differentiation. So I'm going to kind of walk through the process here of implicit differentiation. So starting with the equation x squared plus y squared equals 1, notice we have x's and y's all mixed together in one equation, right? You don't need to isolate y in order to find dy dx. So instead what we'll do, the first step is I'll apply d dx to both sides of the equation. Okay, so it really just looks like this, applying d dx to x squared plus y squared, and then applying d dx to 1. So what we're taking the derivative of here is the function x squared plus y squared, and what we're taking the derivative on the right side is just the constant function 1. So, well, what we'll do is we'll treat, because we're doing the derivative with respect to x, we're going to treat the y variable as if it's a function of x. So in other words, the chain rule applies. So that means that we multiply dy over dx after taking the derivative of an expression with a y variable. So let's look at that here. So we've got x squared. Well, that doesn't have a y variable. So the derivative of x squared is just 2x. And then the derivative of y squared is 2y. However, we're treating the y variable as if it's a function, as if it's like a function inside of the square. Think of that, that's like our u squared. So applying the chain rule here, we'll multiply by du dx, or in this case, dy dx. So that's essentially just applying the chain rule to multiply this piece here. On the right-hand side, of course, is just the derivative of a constant, so we know that's 0. Okay, so every time we're taking the derivative of an expression with a y variable, we always have to multiply by dy dx. Now the last step will be to isolate dy dx. So, oops. So what I'll do here is I'll just subtract the 2y dy dx term to the other side. Or actually here, let's do it the other way around. So I'll subtract the 2x to the other side. So I got 2y times dy dx equals negative 2x, and then divide the 2y. So I get negative 2x divided by 2y will be just negative x over y. So there we found dy dx, but notice it's in terms of x and y. So, but the nice thing is now I can find the derivative at any point. So given an x and a y coordinate, now I can find the slope of a tangent for any point on the unit circle. So let's apply that here. So suppose I want to find the slope of the tangent to the unit circle at these 2 points here. So let's just use our dy dx formula that we've solved for in the previous step. Okay, so we can evaluate at the point 1/2 comma radical 3 over 2. So negative x over y will be negative 1/2 and negative radical 3 over 2, or just radical 3 over 2. Simplifies to negative 1 over the square root of 3. And you can kind of see how that corresponds here at the point 1/2 comma radical 3 over 2. There we have that negative slope, right? Negative 1 over radical 3 is the slope there. Similarly, if we evaluate at the other point, here is the point here in quadrant 4, got 1/2 comma negative radical 3 over 2. You get the slope will be negative 1/2 over negative radical 3 over 2. So now this simplifies to positive 1 over radical 3. So there we see it's that positive slope. So what we should do is just practice the process of implicit differentiation that we did. We can kind of see how it's useful here. So this kind of saves me the hassle of having to first isolate y and then compute the derivative explicitly. Here I'm just finding the derivative implicitly, and then I can evaluate at any point on the curve. So let's practice that with an example like this. Here find y prime of x when sine of xy is equal to x squared plus y. So the trick that we got to keep in mind here is that actually there are some rules to consider. In other words, sine of xy uses a couple of things. Notice it's got the xy inside of the sine function. So right there, we're thinking about the chain rule. But in addition, you've got x times y, so you're going to also have to think about the product rule. Okay, so think about the two rules that we're going to apply here for sine of xy. But it's the same, essentially the same steps that we did in the previous example. Start by finding d dx applied to each side. And again here, xy is inside the sine function, so we're thinking of the chain rule. So the derivative of sine is cosine times the derivative of xy. And so that's just applying the chain rule there. Over here, we've got d dx of x squared is 2x. And then the derivative of y, well, we can think of that, the derivative of y is just 1 times the derivative of y, dy dx. So I'll just write y prime instead of dy dx. So sometimes it's easier to write y prime instead of dy dx, just to save myself some writing. But now notice here, we've got the derivative of xy here. We're going to need to use the product rule. So you got x times y. So here I'll open it up so it's all grouped together. And since we're applying the product rule, it'll be the derivative of x, which is 1, times y without taking a derivative, plus x times the derivative of y, which is 1 times y prime. Okay. So hopefully you guys see how the product rule applies there, right? It's the derivative of x is 1 times y without taking a derivative, plus x times the derivative of y, which is y prime. now we want to isolate, our goal is to isolate y prime. So I think what makes it easy to do that here would be to just rearrange the terms so that you got all the y prime terms onto one side of the equation and all the other terms on the other side. So I'll distribute out the cosine xy here. So I'll have y times cosine xy. And then I've got xy prime times cosine of xy. And then 2x plus y prime. So let's rearrange the terms. So I'm going to put all the y prime terms onto one side. So here's a little bit of a breakdown of how that's going to go. We're going to rearrange the terms so that the y prime terms are on one side. The other terms are on the other side. So the terms without y prime are on the other side. So essentially that's a good way to kind of think about how we can isolate y prime. So I'll just subtract the y prime over here, and then I'll subtract the y cosine xy over there. So I got xy prime cosine of xy minus y prime equals 2x minus y cosine of xy. Okay. And then I can factor out the y prime over here. And then all I have to do is divide by x cosine xy minus 1 to get y prime by itself. Okay, so after I've rearranged the terms so I get all the y primes on one side, then I can factor it out and isolate it. So here the final version would look like this. Y prime is equal to 2x minus y cosine xy, and then x cosine of xy minus 1. And you notice that y prime, the derivative that we get here, depends on both x and y. So actually what's interesting now is we've got the function y inside of our answer for y prime. So I would need an x and a y coordinate to be able to evaluate this now.
Excuse me, Professor, I have a question.
Mm-hmm.
In the example of like a test environment, would you want us to get the end result like you got y prime equals and then the rest of the equation, or would you want us to just apply the derivative, the respective derivative rules?
I'm not sure what you mean.
Like for example, in the last test, you said we just have to apply the rules, correct? Rather than simplify the equation.
Well, are the instructions, so pay attention to the instructions. Find y prime of x. You need to get y prime equals something.
Oh, okay, I understand. All right, thank you.
Yeah, so Yeah, it's not just like, you know, you can stop like at the third step here. You really have to go all the way, right?
Yeah, that makes sense.
It's more than just applying the rules here. You have to go all the way to isolate the y prime. So really implicit differentiation is that whole process. Okay?
Okay, thank you.
Yeah, so pay attention to the steps that we always go through here. We apply d, so it's like if I'm looking at the process that we looked at earlier, you apply d dx to both sides. Whenever we see a y prime, or whenever we differentiate a y variable, we multiply by y prime or multiply by dy dx. And then we isolate the y prime. Okay, so this is one that you definitely need to practice to get the steps down. But let's try another one. Oh, here you go. Here's the tangent line, right? We want to find the tangent line to the curve x squared plus xy minus y cubed equals 7. And what you can see here, there's the curve, right? It's not a function. So isolating y in terms of x here is going to be too difficult. So what we should do instead is just find dy dx implicitly, and that'll give us the slope of our tangent line. Okay, so here I'm going to, again, just apply the steps that we did before. We'll start by taking the derivative of x squared plus xy minus y cubed equals the derivative of 7. So on the left-hand side, notice that we got something similar to what we saw last time. We were taking the derivative of xy. We have to do the product rule for that one. And so just like before, we're going to do the product rule when we get to that one. Okay. So otherwise, x squared is just 2x. When we get here, we're going to do the product rule. So we have derivative of x is 1 times y plus x times the derivative of y, so x times y prime. So you see that's where we did the product rule here. Product rule. And then minus y cubed will be minus 3y squared times y prime. Okay, and there again, don't forget the y prime, because you're taking the derivative of 3y squared, or of y cubed is 3y squared, but because it's a y variable, you have to multiply by y prime. Okay, so that's the key thing. Whenever you're taking the derivative of a y variable, you always need to multiply by y prime. Okay. If you don't have that there, then you're going to be missing that y prime when you go to solve for it. And then on the right-hand side, the derivative of 7, of course, is just 0. Okay, so actually this one isn't so bad. We can easily just move some terms around to isolate the y prime. So just like before, I'll move the terms that don't have y prime to the other side, or move the terms that do have y prime to one side. So I'm going to subtract xy prime to the other side, and then I'll add 3y squared y prime to the other side as well. Okay. And then over here, I can factor out the y prime.
Professor, does it matter which side you subtract or add the parts of the equation on?
Nope. Just get them on separate sides. Okay, so maybe I'm doing it differently than you would have naturally done it. I'm just kind of doing it in a way so that the minus signs look a little bit nicer. Because if I move these two terms over there, then you'd have minus 2x minus y, which is fine. No worries. Just put them on separate sides. That's all you have to do. And then factor out the y prime. And then isolate the y prime. So here I would get y prime is 2x plus y divided by 3y squared minus x. Okay. And then to get the slope of our tangent, at the point 3, 2, well, I can just put y prime evaluated at 3, 2. Here, so that'll give me my slope. Six plus 2 is 8. 3 times 4 is 12, minus 3 is 9. Okay, so we got the slope is 8 over 9. Just evaluating this guy at the point 3, 2. And then to get the equation of our tangent line, then we can just use the tangent line in point slope form. So the point was 3, 2, so we'll have y minus 2 equals 8 over 9, x minus 3. So we get here y equals 8 over 9x. And then let's see, I get minus 24 over 9, which is actually 8 over 3, so minus 8 over 3, and then add the 2, so add 8 plus 6 is, let me see, okay, so 8 over, minus 8 over 3 plus 6 over 3, so minus 2 over 3. Okay, so just a little bit of simplifying there to get it into the slope-intercept form. Okay, and you can see here what it looks like in the graph. Which of course, again, we can notice that the point here would actually maybe be hard to work with in an explicit form of this equation, because the way the curve is drawn here, you can see it's not really a function of x at that point. Here's another example where, again, here we're finding the slope at a given point. So let's go through the steps of implicit differentiation again one more time. So take the derivative of both sides, right? 2x plus y to the 1/3 power equals y. So we'll apply that to both sides here. notice that on the left-hand side, we get a little chain rule there because you've got the 1/3 power on the outside, and then you got the x plus y on the inside. Okay, so to do the chain rule here, we'll multiply 1/3 times 2. Subtracting 1/3 minus 1, we get negative 2/3. So that's just doing the outer function. And then times the derivative of x plus y. Over here, we'll just have the derivative of y will be y prime. And then finally here, we can take the derivative of x plus y is 1 plus y prime. Okay. And actually, one trick I want to show you guys here that might help a little bit is to notice that here we're actually just trying to find y prime at this 1.44. Like in the previous example, we went all the way through, we solved for y prime in terms of x and y, and then we plugged in the point at the end. But there's no reason to wait until the end to plug in the point. We can, for instance, now that we've taken the derivative, we can plug in the point now, and it might make it easier to isolate the y prime. So this is just a little trick that I think, in this case, because we're just evaluating at this one point, we can evaluate now to make it easier to solve for y prime. Right? Because really all I have to do is plug in the 4 here for x plus y to the negative 2/3. Which is really just 8 to the negative 2/3. And here actually maybe it helps, you can think of that as 2/3 times 8 to the 2/3. Eight to the 2/3 is like, here, let's just remind you guys how to do that. It's like the cube root of 8 and then squared. So it's 2 squared is 4. So I've got 2/3 times 4. So 2/12, right? Or 1/6. So I can really just multiply the 6 to the other side. So I have 1 plus y prime equals 6y prime. And then subtract the y prime, and I get 1 equals 5y prime. So in the end here, I can just divide the 5. We get y prime is 1/5. Which is, notice that it's already evaluated. We evaluated it in a step here. This is where we evaluated it. Oops. So you can see evaluating it at that step just made it a little bit easier to isolate the y prime. And so that once we do isolate the y prime, then that's the slope of our tangent. Okay. So actually, before I do the next one, do you guys have any questions about this one? No? Okay, let's look at this one now, where it's asking us to find the second derivative. So let's think about this idea now. So we showed actually already, so remember how we did this in the first example, how to find the first derivative. Remember we had 2x plus 2y times dy dx equals 0. And then we isolated the dy dx. And we got dy over dx equals negative x over y. So we can apply the derivative to both sides of this equation now to get the second derivative. So we see over here, right, we have the second derivative. Over here, we've got to do the quotient rule. And then the derivative of the numerator will be negative 1 times the denominator y without taking derivative, minus negative x times y prime. Right, would be the derivative of the denominator, and then over the denominator squared. Okay. So a couple things we notice here. We just get everything in terms of x and y, except we also have this y prime term here. So let's do something with this guy now, because actually what we have here is our y prime is just negative x over y. So we can put that in here for y prime. And now we have everything in terms of x and y. Which actually we can do a little bit more simplifying if we want. If I multiply top and bottom by y, I can divide out the y here. So I think it would look something like this. Negative y squared minus x squared over y cubed. If we do a little bit of simplifying there. So that's our second derivative. So you can think of that, that's like our y double prime now.
Do you always want us to simplify it to the negative y squared minus x squared over y cubed? Or could we just leave it as the one before?
Depends. I think, you know, if this were an exam, I'd probably give you full credit for leaving it in this step. But you should know how to do that simplification because it's a very convenient way to write your answers. Looks much better this way than it does this way. Okay, so make sure you know how to do that simplification. But if it's on an exam and you mess up that last step there, you know, I'd be careful with that. Okay.